Hi, thanks for joining me in my session. My name is Jan Bruder and I'm a field engineer at SUSE Germany. Today I'm going to talk about Kubernetes and Container Security 101. Now Kubernetes, like any other highly automated system, comes with its own complexity. So there isn't a single button that we can just push to enable production-grade security. Instead, what we want to do is understand all the moving components, the best practices, and the tools that are available to us to ensure secure operations. So I like to approach this from a container application perspective. So when we look at the container lifecycle, there's a lot that we can and we should do in the different phases. This already starts in the dev build phase, where we put our application in a container, we decide which base images we inherit and which libraries we package with our application. Moving on to the deployment phase, this is where we come up with a set of configuration files that determine the privileges and the level of access the application may have to something like, for example, secrets. And then during the run phase, this is where we may need to detect new threats that occur, like, for example, a malicious process that suddenly runs in a container. And so as you move from left to right, this job gets infinitely more difficult because you may start with a single image during the dev build phase, a single set of configuration files during deploy phase, but you may end up with dozens or hundreds of instances of this image and configuration. And so that makes it much more difficult if you haven't captured any security problems right away to then detect them and to address them once these applications are deployed. So the paradigm of shifting security left really makes sense in this context. Now let's quickly talk about the 5 points that we are going to discuss in the next 25 minutes. We will talk about Kubernetes access control. We will address container security best practices. We will talk about image scanning, container runtime security, and finally cluster hardening. Let's start with Kubernetes access control. So we cannot talk about access control before mentioning that Kubernetes is an API-centric platform. This means that every resource is accessed through a single component, which is the Kubernetes API server. And this is not only true for users, but also for internal components in the cluster. Now, if you want to access resources in the cluster, we are doing this typically by interacting with the RESTful API using something like the kubectl command line interface. And so the level of access a user has in the cluster is directly determined of the privileges he has been granted in the API. And what's also interesting to understand is that the Kubernetes API might not only grant access to the cluster itself, but also maybe to underlying infrastructure like a cloud provider by means of the integration that Kubernetes has with cloud provider and other infrastructure providers. And so if we want to secure Kubernetes, we really need to make sure that we carefully and granularly configure the API access permissions, meaning who can perform what operation on a given API resource. That's how we secure the access to our cluster. And so if you look at the elements of Kubernetes access control, this really consists of an authentication part, an authorization part, and then we have also an admission controller part, which we're going to talk later on. This is what separates a user request from some data being read out or committed to the etcd data store. So what do we mean by authentication? Authentication is the process of establishing a user's identity by validating the provided authentication factors, which could be a username and a password pair. Now let's talk about some specifics in Kubernetes. First of all, Kubernetes does not come with its own identity and user management. This is purposely not implemented in Kubernetes itself. Instead, Kubernetes provides a set of interfaces and a set of authentication protocols that allow you to integrate your user management from an external system. So let's look at some of these protocols that are available here. Or actually, these are the most important ones. So start off by OpenID Connect. This allows you to integrate your cluster with an ONIDC compliant identity provider. Moving on to Authentication Proxy. An authentication proxy is often used to integrate with some of the more traditional authentication systems like an LDAP or an AD or some kind of SAML authentication provider. And in the case of authentication proxy, the user request is not directly sent to the Kubernetes API. Instead, the user request is sent to the Authentication Proxy component, which performs the authentication, and only once that is established, the request is then proxied to the Kubernetes API and returned to the user. Finally, we have a webhook token authentication protocol. In this case, the request is directly sent to the cluster, but with a bearer token that Kubernetes has no notion of. So Kubernetes will send this bearer token to a token validator, which is an external system, to validate it. And if the external system validates the token, then only then the request is further handled by Kubernetes. This brings us to authorization. So this is once we have established the authentication of the user, and we now want to establish if we should grant the requested access to the particular resource in the API. So the default authorization mechanism in Kubernetes is role-based access control. Role-based access control is a method that is specifically based on a user's role within an organization. And what that also means is that it implements the principle of least privilege. Principle of least privilege means that we only grant access to the information that a user needs to perform his job or his role. And we specifically prevent him from accessing anything else that is not necessary. Now, when we combine Airbag with the principle of decoupling that is implemented in the API, meaning that instead of one resource called application, we have many different decoupled resources that are part of an application. When we combine this, we get a means of being able to very granularly define the permissions. And so this is a great security feat if we make properly use of that. So what are the scopes of Kubernetes Airbag? Kubernetes Airbag has two scopes. We can define permissions on the cluster level, and we can also do that on the namespace level. So a namespace is a way to logically separate resources in a cluster by attaching certain policies to it, like access policies, network policies, or even specifying specific resource quotas. And the typical use case for namespaces are when you share a cluster across different tenants and you want to ensure that the tenant resources are properly isolated from each another. There's other use cases. You can use it to define application context, application environments, and things like that. So how do you define Airbag policies? Airbag policies essentially consist of three components. First off, you have a role element. So the role element defines a set of rules that define what permissions can be, or what operations can be done on a specific resource in a specific context. So the context, again, could be a namespace, could be a cluster, and the resources can be any API resources. So if, for example, if you want to grant the privilege to request a list of running pods in a specific namespace, this is an example of how you do that. So the other element is a subject. So the subject could be a user, a group, or it could be even an internal service. And then you need something to map the two together. So you need to map a specific user to a specific role. And this is what's done by a role binding, which is another API resource. And to give this, to make this a bit more illustrated, here you have two of these resources. So you have a role binding and you have a role, and you can see how defining this kind of access consists of writing a couple of lines, maybe like 20, 30 lines. It's okay, but once your container platform scales, you get more users, more environments. Managing these Airbag policies manually actually becomes quite a tedious job, and it's also quite error prone. So obviously, at some point, you want to start by maintaining these YAML files in source control, which solves some problems, but not all problems. Like, for example, how do you ensure that the state defined in the Git repository is actually what is the reality in your cluster? So this is one example where Kubernetes management platform really helps to solve this problem and makes your life easier. Let's move on to container security best practices. So before we talk about best practices, let us understand the default container security that is provided by Linux containers. So what Linux containers allow us is to deploy multiple applications on a single server or VM in a both isolated but also highly efficient manner without all the overhead that we have from hypervisor-based virtualization. Containers provide process level isolation, and they do that by leveraging very standard existing technology from the Linux kernel, such as namespacing and cgroups. Each container is executed in its own namespaces, and because the kernel has namespacing for different kinds of resources like networking and file system, from the point of view of the application, you get a virtualized environment. Now, this is quite nice, but containers also have configurations that allow you to, let's say, make this isolation a bit looser, because sometimes it's just needed that you get elevated privileges even for a process running in a container. So what that means is containers are only as secure as the runtime configuration that you provide when you start a container. Another important aspect is that container virtualization is implemented on the OS, on the host OS kernel. So if your host OS kernel is not properly patched, then this virtualization does not provide very great means of security. Let us look at as an example. So for example, what you need to realize that if your process is root in a container, this is exactly the same root as on the host. So if a malicious process manages to break out of the container by maybe exploiting some vulnerability in the kernel, an attacker will be automatically a root on the host, which is something that we really like to prevent. So a very good practice is to avoid running applications as root user in the container unless it's absolutely necessary. And sometimes it can be necessary, but you have to do it in a controlled manner. Another example is bind mounts. So you know that from Docker, right? So looking at this example here below, we can run a Docker container and you can mount the host file system to it. And with a Kubernetes pod, this is not different. You can do that. It's all the same with a Kubernetes pod. And so by default, there's no limitation on what a pod can mount from the host. It's up to you, the cluster admin, to implement proper procedures and to prevent users from doing these unsecure things. Which brings us to the next point, enforcing container security best practices. They are critical for security because they allow us to protect against things like privilege escalation, breakout attempts like I mentioned before, where you can exploit a vulnerability in the kernel. They prevent cross-container access or host file system access. And they can also help us with limiting the blast radius of misbehaving or buggy applications. How do we actually enforce security policies for Kubernetes? This brings us back to the admission controller part that I mentioned in the beginning. An admission controller is basically a plugin mechanism that allows you to intercept any API calls that come into the system and then inspect them and decide whether you want to grant them. There's two types of admission controllers. There's validated controllers that can grant or deny a request. And there's mutating admission controllers that can actually change the request. So for this purpose, we're just talking about validating admission controllers. And in Kubernetes, there's one built-in admission controller that's there out of the box that you can just use, which is called which is admission controller for pod security policies. Now, pod security policies are actually deprecated as of the latest Kubernetes version, but nonetheless, I want to talk about them. So why do I still want to talk about them? Well, first of all, they're just deprecated. It doesn't mean they are removed. So they will still be in Kubernetes for probably the next 2 years. So you can still use them. Secondly, pod security policies, while opinionated, they can serve very well to understand the mechanisms and the best practices for pod configuration. So they're very good to learn about what the critical configurations are that you have to watch in your pods. Other means to enforce security policies come from community projects, so out of tree projects from Kubernetes. This includes things like the Gatekeeper, projects like Caverno and kubewarden, which is a very nice project which was announced at the KubeCon actually. So I suggest you to look into it. And then obviously you could also build your completely own admission controllers, both validating and mutating, to implement any kind of policies. So let's circle back to pod security policies. So pod security policies are eventually a cluster level resource that you can use to specify the conditions that a pod must met in order to be accepted into the system. The policies are, as I mentioned, enforced by an admission controller that looks at the specs of each pod that is entered into the system and compares them against all available pod security policies. If none of the available policies matches or allows the pod configuration, then the pod will be rejected with an error. And this is how we can automatically implement security policies. What is also nice is that you can use this to allow different levels of policies based on application context or environment. So for example, for a dev environment, you can be less strict, and for a prod environment, you can implement more strict policies. And again, to make this a little bit more illustrative, if you look here, you have defined on the right side a pod security policy. What this policy does, for example, is it specifies that all of the pods, in order to be accepted, they must have the privileged configuration options set to false. So if the developer on the left side creates a deployment with a privileged pod, it would be automatically rejected into the system and an error would be returned. Let's quickly talk about Open Policy Agent Gatekeeper. So this is an open source general purpose policy engine. So it was not specifically built for Kubernetes, but Open Policy Agent, by means of the Gatekeeper project, is now also integrated in Kubernetes. And what's nice about Open Policy Agent is that it comes with its own declarative language. So other than the pod security policies, which is completely opinionated and gives you just a basic set of on and off switches, with Open Policy Agent, you can define your own policies using a declarative language. If only this language, you need to learn it. So it's not a standard high-level language that you might already know. So that's maybe the downside of it. And what's also great is that you cannot just enforce rules for pods, but you can enforce rules for any other resources in Kubernetes. So that's again also something that is enhancement if compared to pod security policies. So Open Policy Agent Gatekeeper consists of two resources. First of all, you have a constraint template. This allows you to define a policy logic and a schema in a very generic manner without applying it to application context at the same time. So this also allows you to even provide input parameters to slightly adjust the policies during the deployment. And so because that is a very generic way to define things, it serves easily also to be shared across different users or across different environments. And then the second part is the constraint. So the constraint is how you instantiate a template in a specific context, for example, in a specific namespace or a specific cluster. The constraint must define the API resources to which the template should be applied. For example, I want to apply it to pods or to ingresses or to secrets. And for namespace scope users, it must also define in which namespace the specific policy applies. Let's move on to container image scanning. Before we talk about image scanning, let's mention some general good practices for image security. So first of all, ensure using up-to-date base images. So this is very important. Typically, there's always some base image in play, whether that's a base image providing your language runtime or a base image providing a minimal operating system. Make sure you're using up-to-date base images so you're free from any known vulnerabilities in something like shared libraries or so. The second best practice is keep your production images clean and lean. Don't include debugging tools in your production images. Don't put things like curl in these images. These will just allow an attacker to exploit even more the container. There are other means to debugging containers which don't involve putting stuff in there that you don't need for your application. use that. Don't put these tools in your production images. Generally enforce best practices during the CI cycle. So there are linters for Dockerfile, for example, that you can include in your CI pipelines. And then also, do something like assessing the image provenance during deployment. So this means, ensure that images are only deployed from a specific registry that you trust. And this, again, is something that you can easily implement with an admission controller, specifically with something like Open Policy Agent, that checks every pod for whether the image is stored in a trusted registry. Now to container image scanning. So container image scanning is critical to ensure that the containers that you deploy into your environment do not include any vulnerabilities that at some point may affect the application security. Scanning a container image means analyzing all the layers of the image and the contents and detect vulnerable components or different other security issues. The most common form of scanning involves comparing the contents of an image against a database that includes CVEs. So when should you apply image scanning? Obviously, you can't do it often enough. It should start at the CI/CD pipeline. So this just implements best practice on the developer application team side. Refuse images that fail your scans. They should not be released. And then finally, you can scan images when they enter the registry to make sure that at least while the images are on the registry, you don't have any ones containing CVs. And finally, you also need to continuously scan images when they're deployed, because there could be CVs, that were not known at the time, but once your application is deployed, they come known later. So you need to continuously scan also images while they're deployed, even if that's probably the harder part. So what tools are available for image scanning? We have open source standalone scanners like Glare, Trivi, Cribe. These are tools that can be used as command line scanners, which can be easily integrated in a CI system. And some of them also work as servers, so they can be integrated in different ways. We have obviously SaaS offerings, like the ones mentioned here. And we have the container security solutions that all typically have some kind of image scanning built in. And finally, we have the image registries themselves. Most of the image registries, open source like Harbor or even enterprise products, they all include some kind of image scanning. Let's talk about container runtime security. This is kind of the holy grail of Kubernetes security because it's the hardest thing to implement. So the goal of container runtime security is to detect anomalous activity in running containers that might impact the security of the cluster and application. And how that is typically done is that your solution is monitoring system calls, network traffic patterns, the processes, and the file activity of containers. And this may be used to determine, there's maybe suddenly a malicious process running that shouldn't be there. Or maybe your server process is suddenly establishing network connections to the internet that it shouldn't typically do. So these are the kinds of the patterns that you want to detect with container runtime security. The scanning is oftentimes based on doing some further profiling of imaging to establishing a baseline of, for example, what system calls your Nginx container is typically doing, and then comparing that against reality. Or you can also obviously define some user-defined rules to detect security problems. There's different ways you can then act on detected anomaly. This could be by just triggering an alert in sort of like a passive protection, or if it's a very critical anomaly, it could even result in the termination of the affected pod. And so the solutions to implement container runtime security, they include open source tools like Falco. And there's actually a talk at SUSECON about Falco, which I recommend to check out. And obviously, there's many commercial container security solutions available that also provide this kind of functionality, which I mentioned before. Finally, I want to talk about cluster hardening. So cluster hardening is sort of like the infrastructure hardening part here. So it starts with hardening, securing the host OS. This might not be the most obvious because, well, we are running everything in containers, right? But the host OS is where we have our kernel, which provides our isolation of containers. So it's very critical that this is properly patched against any security issues. And what's nice is access to the host OS. I mean, this is not really a topic, right? Because no one other than the Linux admin should have actually access to the host, because all other users, they leverage Kubernetes via the RESTful API. So that's the easy part. The general recommendation is, again, to keep your host operating system lean and clean. Maybe use a minimal OS, remove any system daemons that you don't necessarily need, just to reduce the attack surface and also to reduce the necessity to do patching in your operating system. The second recommendation is you need to keep up with Kubernetes release cycle. Kubernetes has a very fast release pace, which is great because you're getting all these new features and increased maturity. But it also means that there's a new minor release every 3 or 4 months. And other than maybe your operating system or other enterprise software that you have, there's no long-term support version for Kubernetes. So that means that any version that you might run, any minor version that you might run, is only ever supported for a maximum of a year with security releases. So we really need to implement good processes to roll out Kubernetes upgrades, and hopefully do that in a way where you don't need to plan for downtime for your applications. So find a good Kubernetes distribution that gives you like zero downtime Kubernetes upgrades. The last point is hardening the cluster itself, hardening the critical components of Kubernetes. And this is maybe a difficult one at first look, because Kubernetes, as I mentioned, is a complex system. It is comprised of many different services, and each service comes with its own set of configuration files, and probably the overall number of configuration files, configuration parameters goes into the hundreds. So how do you figure out what's the best way to configure that system? How do you properly harden that? That's a good question. So luckily we have something to help us here. So the Center of Internet Security is regularly publishing the Kubernetes Cs Benchmark, and this is sort of considered the de facto standard for creating secure clusters. The benchmark basically identifies possible attack vectors, and it gives you very clear guidance on how to mitigate against them by telling you exactly what configuration parameters you have to tweak in what way, and how you have to configure your host operating system. Obviously, so the CIS guiding is basically a bunch of controls, a document that you need to go through, and you probably don't want to really go over this whole document and then manually compare your system against it. So a good way to implement CIS benchmark is by way of automating the task of evaluating the cluster against the benchmark. And you can do that by running an automated scan. So this will give you a report that will point out all the failed controls in the benchmark and also how to address them. And the nice thing is, if you have this kind of automated scan, you can run it at any time. You can run it once during the go live of the cluster, but you can run it also at any time to protect against configuration shift and to ensure that you're always compliant. And what are the possibilities to run a benchmark? So you have Aqua Security KubeBench, which is an open source project, which you can use as a standalone scanner and scan any cluster. And you also get CS Bench integrated in Kubernetes management platform, like, for example, Rancher. So these are the ways you can make use of CS Benchmark. And this concludes my session. I hope you have learned something, and I hope you enjoy the rest of SUSECON. See you soon, and have a nice day. Bye-bye.